All right. Okay, welcome back, folks. So we're continuing today with our lecture about global illumination and path tracing. And last time we got up to the beginning of path tracing. Okay, so as a reminder, if I rewind a couple of slides, we talked about Russian roulette, which is a way to randomly terminate a recursive function call in evaluating a Monte Carlo integral. And that gave us an unbiased Monte Carlo estimator that completed in finite time for this infinite dimensional integral. Okay. And we developed this sort of simplistic recursive algorithm for trying to evaluate this Monte Carlo integral over paths of rays traversing through the scene. And we just finished adding in Monte Carlo, Russian roulette rather, into this part here. Okay, so I've written this up and I said, okay, so this is this will be unbiased. It turns out we proved that in Russian roulette, and it'll actually finish computing this function. It won't be an infinite recursion, but it's still going to be extremely noisy. And I reminded you visually about the kind of noise that we can see in Monte Carlo integral estimation from the Monte Carlo lecture. But actually, that previous implementation pseudocode, if you actually tried to run that, you could write a function like that and export it in your assignment. But if you actually tried to run it, it would be so noisy, so incredibly noisy. It would be kind of unworkable. You would need so many samples to drive the noise down. That's where we got to path tracing. So path tracing is a further refinement of that recursive function call to evaluate the infinite dimensional, infinite bounces of light integral. And the overview on it is like this. Okay, so what we already covered, we're going to terminate these ray tracing paths through the scene randomly with Russian roulette. The next thing, and this is the key for really driving the noise down through these careful engineering choices, we're going to partition the recursive radiance evaluation so that at each point on the light path, that is at each bounce of light recursively, we're going to break it into two partitions. The first one is going to be to evaluate what we call the direct lighting. This is lighting that comes from a light source directly to that point in the light path so far. Okay, so we're going to connect the light path directly to light sources. This is going to be non-recursive, and we're going to use importance sampling over the lights, as we saw in the Monte Carlo lecture, in order to do low noise estimates of that contribution for that portion of the ray path. The second partition is what we call indirect lighting. This is the recursive part. Okay, we're going to recursively keep tracing the ray and make it longer and longer. And when we do that, we're going to importance sample the BRDF, the reflection function. That is, we're going to try to choose rays of light randomly in the direction where the reflection function is bright. Okay, a lot of light is reflecting into the paths that we care about. When we do this, we're going to use Monte Carlo estimates for each of the partitions separately. Okay, it's possible to take just one sample for each of those two partitions that I talked about and just have a ray path that gets longer and longer recursively. But you could also sort of, choose two recursive ray paths, sort of two random directions in your Monte Carlo estimate, and you end up with more like a tree expansion. In any case, we're going to assume hundreds or thousands of paths that we sample through every pixel in the final image. So we're going to average hundreds or thousands of these kinds of samples. I'll show you some examples of those pictures when I complete the description of path tracing. Okay. Anyway, that's the overview. Break it up into two parts: direct lighting, indirect lighting, and sum it up. Now I'm going to try to write all this down in pseudocode for you so we can see it mechanistically. And to do that, we're going to need to make sure that we bookkeep all of the bounces of light carefully so that we don't miss any and we don't double count any. So to do that, I want to just walk you through a way to count that. Okay, that's kind of, once I present it, there's not a lot going on here. It's very simplistic, actually, but hopefully it's a simplistic way of showing it and showing this bookkeeping and how we're going to use it in the recursive function calls in a way that we can be convinced that we're, getting the counting exactly right. So let's come back to this picture. We have an I point where we're going to make the picture, right? We're synthesizing the picture. Here's the ray corresponding to 1 pixel. Okay, so let's say some pixel on the image plane and a ray at that X position going in a direction omega into the scene. And we want to know how much radiance is summing in from the scene, from all the light sources through the infinite balances of light over the scene surfaces out along this one ray into this pixel. We first trace it into the scene, find the first hit point in the scene on this point P, and the light that's outgoing from this point P in the negative omega direction is going to be the radiance that is finally terminal at that pixel. So estimate radiance in at X in the direction omega is the same as estimating radiance out at P in the direction negative omega. The next thing we need to do is to sum all the paths, all the light paths that go through P, representing 0 bounces of light, 1 bounce, 2 bounces, 3 bounces, and so on up to infinity. 0 bounce means, right, that it's not bouncing. The light must have come from this position P itself, which would mean that, which could only be true if P was on a light source. Okay, so that would be light that's emitted at P towards negative omega. Okay, so we'll handle that case separately. 1 bounce means, if you look at this, it has to mean that from P, light came directly from one of the light sources in the scene. In this cartoon scene, there's only 1 light source over here, but if there are multiple light sources, any of those light sources directly onto P and then reflected in this negative omega direction. This is what we call the direct illumination, and maybe you can see why. It's because that first point P in the world that we see, it's directly illuminated, and we calculate that intensity directly. Very similar to what we did in the Monte Carlo lecture. The last one that we'll need, because we're going to handle the rest recursively, is 0 bounce, 1 bounce, and then strictly greater than 1 bounce. If you think about this for a second, it means that that light path must consist of light that starts at the light source and then goes to at least one other point before it goes to P and then out in the negative omega direction. We call this indirect illumination because you can see that the point P is being illuminated by reflected light at some other surface position that's not a light source. It's light that's indirectly reflected from light sources over other surfaces onto the point P. So strictly greater than 1 bounce from light, it means light. It means a light path that goes from the light to P prime to P to negative omega. And greater than 1 bounce at P to the negative omega direction is equal to at least 1 bounce, that is greater than or equal to 1 bounce, towards P from all other points in the scene. For example, P prime, P double prime. Okay, so that's the way that we're going to bookkeep it. Again, 0 bounce, 1 bounce, strictly greater than 1 bounce, and an observation that's strictly greater than 1 bounce at P towards negative omega is equal to at least 1 bounce towards P from some other point in the scene. Question I got here. If P is not a light source, wouldn't bounce 0 be bounce 1? The eye would only see the P. To clarify that, let me clarify the counting here. Okay, the counting is from point P towards the final pixel that we care about. So 0 bounces means that light didn't bounce anywhere in the scene. It just originated from this P going straight to the light source. So if there was a contribution there, they may or they may not be. If there was, it has to be because P is on a light source. That is, this thing here is itself emitting light. If it's not emitting light, it doesn't mean that it's going to be 0. It just means that light's going to bounce in from these other light paths that I enumerated. Okay, so let's try to start drawing this out in pseudocode, okay? So I'm going to use exactly that 0 bounce, 1 bounce, greater, and then greater than 1 bounce that I showed you earlier. So let's do it. Estimate the radiance in at a point X in a direction omega. The first thing we do, as I showed in that cartoon, was we find the point P in the whirl, where we trace the ray that begins at X, goes in the direction omega, right, and goes down to the whirl, so intersects scene with that ray. And then we just do exactly the counting I described. Okay, return the 0 bounce radiance at the point P heading in the direction negative omega, plus the at least one bounce radiance from position P going in the direction negative omega. We're going to look at least one bounce in the next slide, but let's just handle the zero bounce case right here. It's very simple. Zero bounce radiance at the point P going in some outgoing direction omega O just asks us to consider whether P is a light source or not, and asks us to look at P dot emitted light in the direction omega 0. If P is not on a light source, this is going to be 0. If it is a light source, then the light source will tell us how much light, how much radiance is going in that particular direction. Okay, let's look at the at least one bounce radiance case. Okay, so here it is, the function at least one bounce radiance at the point P heading in direction omega O. And we're just going to break this up into one bounce radiance at that point P. And then, as I said, it's going to be at least one bounce radiance from some other point in the world P prime towards P. Okay, so that's going to be the recursive call, because of course, at least one bounce radiance is a recursive call to this function. So let's walk through those 2 points. Okay, so L equals one bounce radiance P omega O. One bounce radiance is right here. One bounce radiance at the point P omega O, this helper function is going to be returned the direct lighting by sampling all the lights. We're going to look at that function on the next slide. Okay, but that's all it's going to do. It's going to importance sample the lights and then try to figure out how much light is arriving at this point P and then being reflected out in the direction omega O. For the recursive part of this call, what are we doing? This is actually a lot of the stuff here is the stuff that we saw in the previous pseudocode. Okay, we're just going to importance sample the BRDF. We're going to get incoming direction omega I and the probability that we chose that by curring to the current point P, looking up its material BRDF, and then asking that BRDF function to give us a random direction omega I and the probability of it. Okay, by doing asking it to perform that doing that random sampling. Then we have to find the point P prime, which is, okay, I have an incoming direction to the point P coming from some point in the world. So I take point P and I trace it back in the direction, the incoming direction, and say, oh, what was that point that is struck in the world? Let me take you back to the cartoon to show you what that looks like. Okay, so we're just P here. And we say, I'm going to choose, by importance sampling the BRDF, choose some direction, random direction. Let's say it was this direction up here. We say, oh, from the point P going in that direction omega I, what's the hit point? I find P double prime in this case, or P prime in this case. Okay, it's choosing some random point. So let me go back to the pseudocode. So that's what this line is doing here, finding the intersection point in the world for the next point along this infinite bounce path. Then we have Russian roulette. We find the continuation probability, just as we did in the previous pseudocode. Then we terminate randomly. We choose a random number from 0 to 1. And we only continue the recursive call if that's less than the continuation probability, right? If it's greater than the continuation probability, then we just do nothing. Okay, we just return increment 0 light in this case. Okay, and then, but if we did continue using Russian roulette, then what we do is we take the radiance from the one bounce case and we increment it by at least one bounce radiance. And now we're saying, give me the at least one bounce radiance that comes from the next point in the in this path of light. That's going to be at the point P prime randomly chosen and going in the negative direction towards P, which is negative omega I over here. And then we have all the other terms in the Monte Carlo estimator. We multiply by the BRDF term. We multiply by the cosine Lambert's law term. We have to divide it by the PDF of choosing that, the probability of choosing that direction. Okay, divide by PDF here. And we have to divide it by the Russian roulette continuation probability CPDF in order to maintain an unbiased Monte Carlo estimate. And that's it. Then we return L. Okay. So for completeness, let's look at just this direct lighting case here. So direct lighting, sampling the lights at a point P, outgoing in direction omega O. We go to the lights and we sample, ask it to give us a sample direction at that point P. So we get the radiance coming out of the light in the direction omega I and the probability that we chose this random direction omega I. Then we have to trace a shadow ray because we picked a point on a light source and we don't know if that light source is directly visible to the point P that we care about. So we have to trace a ray ask the scene to trace array for us from P in the direction omega I and see if it hit something, an object, before it hit the light. If it did hit an object before, it means it's blocked. So then zero light will transfer along this light path. So we return zero. Otherwise, we return this contribution, which is just our familiar set of terms from inside the reflection equation integral and divided by PDF for the Monte Carlo estimator. There's a little comment here. It says, note, this is asking you, this particular pseudocode takes one random sample over all the lights, right? It goes to the lights here and then says, give me one random sample location. In assignment 3.1, we're going to ask you to do something a bit different. We're going to ask you to loop over multiple lights and take multiple samples. I have a later slide to comment on that, okay? But both of these will be unbiased estimates. This is taking one random sample. You'll take multiple samples over the surfaces of all the lights. Okay, so that's it. That's path tracing, okay? Very much like the recursive Monte Carlo estimator with Russian roulette, but we partitioned it into the two parts that I showed you, the direct lighting and then the indirect lighting by importance sampling the BRDF. What does path tracing look like once it's all said and done? We've seen the kind of pictures before. I stuck another one in here. Okay, so this is direct lighting only. That's only 0 and 1 bounces, missing all the higher bounces of light. And this is it with path tracing, so with all bounces of light. Okay, so again, before direct lighting only, and then this one with path tracing or global illumination. And of course, the thing to look at is the infilling of all the shadowed regions with light that has been interreflected from this courtyard and the various objects in this courtyard into these kind of shadow regions. Path tracing, as I mentioned, usually requires a lot of sampling. We need many, many paths that will trace into the scene. So let me show you a picture of what that looks like. Here's some kind of indoor scene here in this courtyard of this building. This is what happens if you take one sample path per pixel. So for every pixel in this scene, we're tracing one ray into the scene, and then it'll bounce, hit a point in the scene, take a direct lighting term, bounce again according to importance sampling the BRDF, and so on and so forth until it's terminated by Russian roulette. But we only get one path per pixel. It's very, very noisy, as you can see. If we take 32 samples, 32 paths per pixel and average them Monte Carlo wise, then we get a picture that looks like this. And if we take 1,000 samples, then it looks like this. Okay, so this is the way in which Monte Carlo of this very high dimensional lighting integral is going to play out through averaging and noise reduction by taking many samples. I see a couple of questions. Yeah, if we take all the bounces, why would we terminate? Because of Russian roulette? Yeah, that's exactly right. We probabilistically randomly terminate each recursive call through Russian roulette. And you have to reason it through, but it's true that that's going to give us a finite number of, and the expected number of function calls, recursive function calls is going to be finite, so we'll finish. What happens if the sample bounce for the greater than 1 check hits a light? Oh, great question. Do we just ignore it? Oh, that's such a great question. And it is a subtle counting argument. Let me try to go back here. So I think the question that Brian is asking is, hey, what happens if, okay, let's follow this path. Okay, so we got the 0 bounce case means that P was a light source, went in. Okay, great. And then on the previous slide, I showed the 1 bounce case is from a light source directly to P and then bounce to the light. And I think Brian's asking, what happens if, as we take this recursive call, if the sample here bounces onto some object that is itself a light source? And okay, so a couple of things about it. No problem if it does that, and that will happen in general, okay? One question, I guess, that's maybe implicit in what Brian's asking is like, well, but if that's a light source, don't we need to take the emitted light from that path into this? The contribution of that into the scene as well? And the answer is no. And the basic reason is because we will account for that contribution by this sampling of the direct lighting, which goes from a direct light source onto a point P, okay? But I like the question a lot because it gets to the core of asking, well, in doing this recursive function calls, have we dropped any paths that we're supposed to count, any number of bounces of light in this path enumeration? And how do we know about that? So I think it's a very good question to reason through, but I tried to explain what I believe the answer is and the core, the crux of the reason why. Very good question, though. Okay, I got another question. Is the main purpose of this brightening images by casting light into the scene and mimicking the behavior of rays bouncing off surfaces in order to brighten the image and its shadows effectively? Yeah, great question. I mean, I showed this example. Is the purpose of global illumination to sort of take these very dark regions and fill them in? And it is, in a lot of ways, that's one of the primary visual effects that we notice is this interreflections of light filling in shadow regions, but it is not the only one. One example of something else is something that I described called caustics, that you can see, you know, as sort of concentration of light refracting through optical surfaces and concentrating either by reflection or refraction across curved surfaces. Another one is a color bleeding. You can notice that this green wall over here has filled in this shadow. Notice the shadow looks very greenish over here. You can notice that the red wall over here has created a red cast in this dark shadow over here. More generally, what this global illumination solution is attempting to do is to account for all possible visual effects, all possible lighting visual effects that appear in the real world by physically simulating in an accurate way all of the light transport that occurs from light sources, multiply reflecting across all the surfaces in the scene before they arrive at the camera. Okay. So lots of paths needed in order to create low noise images, which you'll find in your assignment because you'll write your code and then you'll try to run it with, you will choose how many paths to run and you'll see the effect that it has on the noise. Are there some quantitative ways to check how many samples each pixel should take, or is it just 1,000? Oh yeah, or is it just 1,024 as a magic number? 1,024 is not a magic number. It will totally depend on the scene that you're tracing, its distribution of light sources, where they are, how well they're blocked in the scene, the size of them, area of them, the intensity of how small their point sources are, things like that, the material types in the scene, the visibility and complexity of the geometry in the scene. All of those things will come into play. It's a very good question whether there's a way to check whether you've got enough. There are statistical methods. Since this is Monte Carlo, I haven't talked about it that much in this class, but you know that the Monte Carlo estimator itself is a random variable, right? So as you draw samples, you're going to get an estimate. The mean of that is going to be the estimate of the integral that we take. But you can, by drawing samples, get an estimate of the variance of your Monte Carlo estimator. That's a way of saying that you can run the statistics as you're computing that Monte Carlo estimate of how well you think you're doing, how noisy you are. You can use those types of statistical methods in order to determine how much further you want to go, how much you want to drive the noise down or drive up the signal to noise ratio before you stop. Let me summarize the intuition on global illumination and path tracing. Okay, so summary. We used operator notation, right, last time algebraically, and that led us to the insight that the solution is adding successive bounces of light. To do this, we're going to trace n paths through a pixel and sample the radiance in the scene using our ray tracer. We're going to build paths by recursively tracing to the next surface point in the scene and then choosing a random reflection direction. At every surface that we touch, we're going to sum the reflected light into this ray path. And we sum the emitted light for the first bounce. How do we terminate paths and avoid infinite recursion? We use Russian roulette to kill the recursive function calls probabilistically. And how do we reduce noise? We use importance sampling in choosing the random direction. We do that in two ways. We importance sample the light sources and we importance sample the BRDF. Of course, we also take multiple paths, trace multiple paths and average them in order to reduce noise in the standard Monte Carlo way by taking more samples. Okay, so that is path tracing and that is global illumination. That is by far not the end of the word on it. Path tracing was the first and most classic global illumination algorithm. There are many others that have been developed that have other strengths and weaknesses. Some are called bidirectional path tracing. Some of them are called photon mapping. there's beam tracing. There's a whole bunch of different variants of this kind of thing, but they all began with this understanding of what the lighting integral was, this intuition about infinite bounces of light and how to solve or how to estimate those using Monte Carlo integration. Okay. Let me give you a few implementation notes that are going to be helpful to you on your assignment. Let me start with the light source thing that I mentioned before. So consider if you have multiple lights in the direct lighting estimate. So not just the one sun that I've been sort of drawing in some of these cartoons, but let's say that, you had like 5 or 6 area light sources in the scene, which is pretty typical. One strategy can be to loop over all n light sources and then some Monte Carlo estimates for each of those lights. So for each light, you could compute a Monte Carlo estimate of its lighting contribution by taking m samples, for example, over the area of that light with importance sampling. If you did this, because you have n lights and m samples per light, you'd have n times m samples overall. This is what the assignment is going to ask you to implement, okay? And this is a perfectly reasonable way of doing it. As I mentioned in the pseudocode, a different way is to take a single sample. So, and I just said, well, we'll ask the light sources to do that. We'll say, lights, give me one random sample. Let me just walk through a bit of detail about how you could imagine doing that. You could consider random sampling all of the n light sources with a single sample. The way you could do that is you could randomly choose which light I you're going to sample from with probability p sub I. So you just choose one of them. Okay, choose one of them randomly. Secondly, you can randomly sample over that light, that particular lights, the ith lights area or directions that that we would point in with probability p sub L. So the probability of choosing that specific sample is going to be p sub I times p sub L. And then we will weight the lighting calculation that we do for the amount of radiance emitted by that light at that position by dividing by pi times pl, because that's the probability of choosing it. Would this estimator be unbiased? Absolutely. It will be a one sample Monte Carlo estimate for that integral. How would you importance sample intelligently? For example, if you have I light sources, well, if you could sort of tell one of them is much bigger and brighter than the others, you might choose to make the probability of choosing that a lot higher. You might even sort of take into account whether it's closer to the point that you're illuminating or not, because if it's closer, its solid angle might be larger and the transfer of light energy will be higher. You could do all those kind of things in setting up the probability that you use for each of those light sources. And of course, this is for a single sample. You could just repeat this n times and average n such samples, and that would give you an n sample Monte Carlo estimate using this scheme. The second tip that I want to give is about point light sources and ideal specular materials in the scenes that we choose. These, of course, come up all the time because we use point light sources and we use perfect mirrors and perfect glass in our scenes all the time because we do that kind of rendering of those kinds of scenes because they're fun to draw, fun to make pictures of. But it presents a certain sampling problem that we have to take into account. Okay, so the problem with these idealistic light sources and materials is that if we're going to sample directions randomly, okay, like we choose a random point that on the hemisphere as an example, we're going to have zero probability of matching the exact direction that a point light source is located, or zero probability of exactly matching the perfect mirror reflection direction, okay, off a mirror surface or off a glass ball if we use random sampling in direction. The remedy for this is to special case these materials. They really need to be special cased. You can sort of think of them, if you like mathematically, as having like a Dirac delta function, light distributions or reflection functions. So in direct lighting, we will importance sample the point lights by generating a single sample pointing directly at each point light source. We only need one sample. We don't need to do it n times, right? Because it's once we have one point light source pointing at one sample direction pointing directly at the light source, we're done. And in indirect lighting, in path tracing, we will importance sample specular BRDFs by generating a single sample that goes exactly along the specular direction. The specular is the perfect mirror direction for mirror surfaces. And for refraction through glass, for example, it's the perfect refraction transmission direction. Okay, so we'll special case these. The next tip I want to give is about numerical precision. Numerical precision, because we're using floating point of which is represented on our computers with a finite number of bits, is really significant in lots of numerical computation and is really significant in ray tracing. Let me show you the most classic example of problems where it comes up. Let's say that you have some sphere out in the world, okay, some sphere with this radius of 1 and this specific center, okay, 1930.420, and some y position, similar decimal places, okay, out here in the world. And consider calculating the ray intersection with a specific ray pointed at that sphere, okay? The actual sphere intersection you might get might be something like this, 1930.4196, blah, 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 blah. But the true intersection mathematically might be something like this, 1929.7203, blah, blah, blah. This is the kind of finite precision floating point error that can accumulate, especially when we have certain functions that we need to solve in computing a ray sphere intersection, such as a square root, for example. The problem with that is if we get the intersection with a surface wrong, in the sense that it's numerically off, something that can often happen is that we end up with this picture where we trace a camera ray, we calculate a surface intersection, but the numerical intersection point that we got is actually a bit too far and is actually below the surface. This happens a lot. If this happens, then the problem that occurs is that if you try to trace from this point towards the light source to calculate the direct lighting in the path tracing integral, you're going to trace the ray towards the light source and you're going to hit the surface itself. Okay, this is a very short distance away here, but you'll calculate that there's a hit point. So you'll calculate that you're in shadow and no light will transfer. And that will manifest as a lot of like incorrect shadow sort of splotches. So you can see on the left-hand side, the lack of these splotchy noisy shadows. And on the right-hand side, because of floating point precision issues, you can see there's sort of a gray sort of speckliness to this, which should actually be a pretty close to even white square, some very dark regions, and even in these spheres over here, some really noisy sort of things going on. This is because of this floating point precision issue that I described. So what are some remedies for that? One of the ways is that you could increase the precision. Okay, we could use 64-bit floating point instead of 32. This would give us like 53 bits of precision instead of 24 bits, in our decimal places. This would increase the memory footprint and the cost of doing these calculations, but this can help. It can't entirely make this problem go away, though, as you might guess. We could ignore re-intersection with the last object that we hit. I sort of said that if we hit a surface and find it's a little bit too deep, when we cast that ray towards the light source to test whether we can see it unoccluded, we're going to hit our own surface is the problem. So we could just say, well, I'm going to do that shadow ray, but I'm going to never test for intersection against myself, against my own object. This is sort of a special case that can help a little bit, but it really only works for like flat objects like triangles. And it's no help if our model has things like, multiple coincident triangles or other sort of common cases that arise. So this is something that can help, but it's sort of an incomplete solution. Another approach that's pretty common is to try to offset the origin along the ray to ignore close intersections. So for example, here we could, if you follow this picture, we could say, well, before tracing towards the light source, I can just try to offset it a bit in the positive direction to try to get clear of any things that might be within my numerical precision, imprecision window. Not a bad idea, but it turns out it's hard to choose that offset without making it too small or too big and creating other visual artifacts. Okay, so what's a good remedy? Some of those can help. This is another remedy that can be pretty good. You can take the intersection point that you numerically calculate, and then you can project it onto the surface position of the closest surface. Okay, as you can see here. Project it onto the closest point on the closest surface. It turns out that this is something that helps visually quite a lot, okay, as a tip. All right, almost done with this lecture. Those are the specific implementation tip comments that I wanted to make. Here's some good scenes for path tracing. I'm just going to wrap up with some photos. Okay, this is a diffuse statue character here and a skylight. It's a really big light source. It gives diffuse shadows, and the infilling of interreflections is visually pleasing. Here's another example of that kind of a thing. And yet another model. This is one last example here. These, as you can see, sort of have large area light sources. They have shadows that get infilled. It can handle a range of material types very well, such as this very glossy material here, as well as very diffuse material sitting inside these complex lighting environments. Here, though, is a challenging scene for path tracing. Earlier, I described that, yes, you can resolve caustics using a path tracing algorithm. In that case, a lot of samples were taken in order to resolve it well. If you take, what's not even a small number of paths here, 1,000 paths per pixel, this is the kind of scene that you would generate for this glass ball with a small area light source up and to the right somewhere. You do resolve a sharp highlight because of the focusing effect of light, but you end up with a lot of these sort of firefly noise, noisy dots everywhere as well. This is very typical, okay, for this kind of a scene, for these kinds of caustics. A good question to ask yourself, and I'm not going to describe why here because I want you to have the opportunity to think about this, is what makes this a challenging scene for path tracing? You'll have the chance of ray tracing some of these in your assignment, but you're going to have to think about it. It won't just be evident by the behavior of your ray tracer. You have to put a little bit of thought into thinking about why do these fireflies and sources of noise show up. Okay. Super good. Let me move to the next slide deck and share my screen. Then get my chat window back up. Here we go. Okay. Anjali, maybe you could help me. I think there's maybe one participant or something that has a not muted mic. I hear from time to time, like just like little noises, I think. If you can help to mute anyone that's accidentally unmuted, that would be helpful. Thanks. Okay. So let me just take a look. Let's see. Anjali answered some questions. On real-time ray tracing. Well, how do we determine when we need to project for this shadow fix-up that I described? You'll get a chance to play around with this on the assignment. But the short answer is that when you write the code for it, you basically will do that projection every time. If you're in a case where you don't have a numerical precision issue, it just won't cause any problems because projecting onto that nearest surface won't move the point at all. But if you do need to do it, then it'll get it onto the surface and it will avoid the next shadow test failing. All right. So I want to move on to the next lecture, which is actually really tightly coupled with this path tracing lecture. It's just going to deepen our look into material modeling. I gave you a mini intro to reflection and material functions in the beginning of the path tracing lecture. So this is just going to get into it in more detail. Okay. And this is neat because this is how we make some of the most compelling pictures, is by having a richness of the types of materials that we can model on the computer and incorporate into our 3D worlds. So what is material in computer graphics? We've talked about shape. Obviously, I'm modeling it with smooth curves and surfaces, as well as polygon meshes. Material, of course, is what are the colors of the objects? How glossy are they? What, is it black coffee or is it like white foam on top of my latte? That kind of a thing. Okay, so it's about the materials. And materials, as we've seen classically in graphics, are BRDFs. We're going to look at and touch on advanced materials as well that break this rule, but BRDFs are the most common material modeling function and structure in computer graphics. We saw some of these diagrams in the mini intro. So let's review. What is this material? Light's coming in along this red ray and then it's scattering in all directions. What is this? A diffuse material. Okay, it's going to scatter light in all directions and it's going to produce objects that look matte, as if they're matte in color and matte in reflection. It doesn't say anything about the color. It could be purple. It doesn't say anything about the texture on the object. It could be this sort of wood grain texture. It really has to do with the characteristic that the objects are scattering in all directions, the light that arrives there. Hence, they have this very soft, matte appearance. In contrast, what's this material again? Light comes in, scatters mostly around the mirror direction. Those are glossy materials, right? This is a glossy BRDF. Copper is an example. Aluminum is another example. What's this material? Light comes in along the red ray and it splits into two parts, one reflecting in the blue direction, which if you look carefully is exactly the mirror direction. And another one coming in here along this green arrow. This is a perfect specular material that has reflective and or refractive components. So things like, plastic that's got a certain thickness in here. You can actually see the underlying inside cube that's contained by this plastic set, clear plastic exterior, and you can see the inside material actually refracting through as well. Similarly here with a partially colored purple material. These are sometimes called BSDFs as opposed to BRDFs. BRDF was bidirectional reflection distribution function, and reflection was light that reflected off in the same direction as incidence. This one allows for transmission, okay, that goes through onto the opposite side from the incident ray direction. So BSDF is bidirectional scattering distribution function, which is a generalization that it allows for scattering too, okay? Okay, here's a picture of perfect specular reflection. I'm just going to spend a few minutes now talking about this because not for the current assignment, but for the assignment after this one, you'll have the chance, if you want to explore different material types, implement different material types and incorporate them into your ray tracer and your path tracer. So here's a light source reflecting off a perfect mirror. You can see the reflection direction. This is the geometry associated with it. It's so simple, actually, perfect mirror reflection, that we sometimes take it for granted. But if you actually have to write a ray tracer to do it, you'll end up understanding it better, than physicists that describe it in a textbook, or if you only thought about it from an artistic perspective before. If you have to do the math, you'll need to do something akin to this kind of vector math. So let me walk you through it, okay? Here is a description of perfect specular. Specular means a single ray in and a single ray out, very idealized reflection in the mirror direction. So the omega I is the incoming direction, omega O is the outgoing direction for this reflection. We know basic things like, okay, theta I here, the angle with the surface normal n, and theta O, they're going to be the same for perfect reflection, okay? They're going to be equal. The next is that there's this kind of geometric structure here. So the key thing is that I'm going to give you omega I, or in your ray tracer, you're going to find you have the omega I, you arrive at a surface position P. From there, you can figure out the surface normal n, and you have to calculate omega O. So how do you do that? You have to do a bit of vector math. The answer you can see here. Where does it come from? The insight is to calculate omega O and plus omega I. Okay, so omega I plus omega O from this ray diagram is going to be a vector that points from the surface up to this point over here. Okay, omega I plus omega O in a vector sense. So how do we get omega I plus omega O? Well, we can note that if we have the surface normal, it's going to be exactly on that direction. And to get to that point up there, we're going to need to add twice this distance here. Okay, that goes up to the bisector. And this distance here is going to be equal to omega I, cosine theta I, right, times this vector n over here. And then we'll double it to get to the top. That's what this is saying. Okay, 2 times cosine theta times the vector n is a vector that points from this point down here to the top. Cosine theta, which is equal to cosine theta I or theta O, is just equal to the omega I direction dot product with the n direction, assuming that those are both normal unit length vectors. Okay, so we end up with 2 times omega I dot vector n times the vector n is equal to omega O plus omega I. Then we're almost done because omega O is just going to be equal to that sum minus omega I. Okay, so we end up with this formula over here. So kind of a neat little way to calculate the reflection direction explicitly. This wasn't so bad. It turns out the next one on refraction is not that bad either, but we'll see a variant of this for the refraction case, which is pretty interesting too, because very rarely, I think in almost any other discipline, do we have to calculate the vector direction for a ray of light that's refracting into some material, into some other transparent material. We're going to do that. If you use the math on the previous slide and put in your ray tracer, you can render objects that look like this. Very nice, highly recommended, looks great. If we do the math for refraction, we'll be able to make pictures that look like these, okay? So specular refraction is just due to light transmitting into some kind of surface like water or glass or plastic. Of course, to do that, we'll need Snell's law. So this is all continues to be physically based. The transmitted angle, okay, omega t transmitted through this interface where so the light enters from one medium and then refracts into the other, is going to depend on the index of refraction for the incident, media and the incident material, and then the transmitting material. In particular, we care about the index of refraction, which are written here as eta I and eta t for the incident and the transmitted. And probably remember Snell's law, easy one to remember. It's just that the relative angles here, theta I and theta t, to the surface normal of this interface follows this law. This is Snell's law. Eta I times sine theta I is equal to eta t times sine theta t. Okay. This is something you could look up in a physics book. You've probably seen variants of this before. As a reminder, eta, the index of refraction for different materials, is like this. Okay, so in a vacuum it's 1.0. In air, it's very close to 1. In water, it's 1.33. In glass, it 1.5 up to 1.6, maybe 1.8 for very special glasses. In diamond, it's a very high index of refraction, 2.4, that leads to, including its dispersion properties, a lot of its the sparkly appearance of diamonds. A question here is, how would the prism case work that I showed over here? Would you have to sample at different wavelengths of light? If so, how does that work going from RGB? Great questions. Multiple questions, good questions embedded in there. Yes, in order to calculate kind of the refracted direction for each of these, you would handle each wavelength separately, because most materials, in fact, really all materials, have different index of refraction, different eta, as a function of the wavelength. So the eta will be a function of wavelength, and the dispersion properties of things like glass, for example, tell us how much the index of refraction varies with wavelength. And to do this, you would sample it according to wavelength. For RGB, that's a good question. Maybe we can take that offline. But since we do calculations in RGB rather than in wavelength, typically, you have to be a little bit careful for how you simulate things like prism, the spread of rainbow light through a prism. Typically, the short answer is you probably want to do it hyperspectrally if you really care about the accuracy of those results. Okay, law of refraction, vector math. Okay, so let's see where I get this. Sorry, give me 1 second. Okay, so this again is the diagram. And in order to calculate this theta t outgoing here, you can follow it from Snell's law. But it's useful to do cosines. We like cosines because they have to do with dot products in the scene, right? So we can take cosine theta I is going to be omega I dot n. So we can get into cosine of the transmitted angle theta t over here is equal to 1 minus sine squared of that theta t. For theta t, we can substitute in, for sine of theta t, rather, we can substitute in from this equation over here, arriving at this form over here, 1 minus eta I over eta t all squared times sine squared theta I. We can convert from sine squared theta I through to 1 minus cosine squared theta I, and then the cosine theta I is, of course, just omega I dot n again. Okay, so that gives us a full formula for calculating all of the facts that we need about the refracted direction. The total internal reflection case is fun to describe and actually needs to be handled as a special case in a ray tracer in order to do the right thing. When light is moving from a optically dense medium to a less optically dense medium, that is eta I over eta t is greater than 1, for example, from water into air, then light that's incident on the boundary from a large enough angle, that's light that's arriving at the boundary from a large enough angle, will not actually exit the medium. The picture is something like this. Okay, so here are these rays, and if you sort of trace the rays back from this underwater diver here that's looking up at the surface of the sea, those rays of light, from a shallow angle will refract out into the world, as you can see drawn here. But once the angle reaches a large enough angle, which for water is about, as you can see, this total angle here being 97.2 degrees, then it will refract to be parallel with the surface of the water. And at any angle that's larger than that, it turns out total internal reflection will happen physics-wise, and that ray of light will actually just reflect back into the water. And if you're underwater, the reflecting back into the deep is often completely black if you're in deep water. So that explains why if you're diving and you look up at the surface of the water, you see the whole sky refracted into a circle, as you can see over here, of a certain visual angle, 97.2 degrees. And everything else is going to look dark because it's going to have total internal reflection back into the deep of the sea. Okay, so that is refraction. Okay, the next thing I want to talk about is a really classic model of material reflection in computer graphics. Very, very common, physically based, and something that is, very visually will simulate in a very visually convincing manner a very large range of materials. This is it's a parametric material model. It's called a microfacet material model. And I want to teach it to you. It has a lot of really interesting characteristics that make us look at the surfaces of materials in a microscopic scale, or at least consider what's going on in a microscopic scale and reason about what's emerging at the visual macroscopic scale because of the finite, the very fine features. Let me start off by showing you a picture. Okay, here's a picture from the International Space Station. Photo that an astronaut has taken of the surface of the Earth. And what I want to call your attention to, okay, is this section of the sea here. You can tell that there's different characteristics over here. It's, of this ocean. See over here, there's you can see the sun reflected. It's up over here, the sun. But in addition, in the sea, you can see reflected. But this is not a perfect mirror reflection, right? If it was a perfect mirror reflection, you would see a circle of the sun, but it's not. What we see is this really broad, glossy reflection of the sun, even though it's reflecting off water. And the reason that we're not seeing, a perfect reflection is that the sea is not, perfectly flat, right? It's not a mirror flat surface. If it was mirror flat water, we would get a perfect reflection. The fact is that the sea is choppy, right? There's waves on it. And because of those waves, which are very, very tiny from this, space vantage point, those tiny ripples on the surface of the sea are creating broad reflections and turning perfect mirror reflection of the water into a glossy type reflection. Okay, this might start to give you some intuition to consider what's happening at a very micro scale and what's going to be the appearance at a macro scale. That's basically microfacet theory in a nutshell. So let's just get right into it. If you have some kind of material, think about what's going on at the microscopic scale. There are microsurfaces, okay, just like the surface of the sea. And for every little micro part of that surface, you can consider which way it's facing. This little micro bump over here, or this side of that bump has a little surface normal direction that's pointing over here. And this little bump over here has a surface normal that's pointing in that direction. These bumps collectively have little, areas that are pointing in all different kinds of directions. Okay, that's the key. The microfacets point in all directions. But if you step away from it a little bit, such as taking a picture from the International Space Station, you definitely have a clear macro surface, right? The surface of the sea from the ISS looks kind of like a flat object. That's the macro surface that we perceive. So the macro scale is flat, but it's rough. The micro scale is bumpy, and at the micro scale, just like the sea, it's actually shiny. Okay, like the sea, if we looked at it closely enough, would look like little mirror reflections, water reflection, little bumps like the waves. Those would be specular. So the individual elements of this microfacet surface act like mirrors, and we call them those little elements. We call them microfacets. Each microfacet has its own normal vector, and when we consider the aggregate reflective properties of this surface, we're going to want to statistically sort of say, well, what happens when all these microsurfaces interact with the rain of photons on that surface to create some kind of distribution of reflected light? What's that surface going to look like? What's its BRDF going to be based on its microsurface distribution or statistical distribution? So the key, as I've already mentioned, is the distribution of the normal vectors of these microfacets. If you have a very concentrated distribution of normals, such as this picture over here, then you'll get a kind of a glossy, a pretty shiny material, okay, like you see on the right. If, on the other hand, you have a very spread out distribution of microfacet normals, like the surface is very rough, so that the normals are pointing in a very wide distribution of directions relative to the macro surface normal, then you'll end up with a diffuse reflection, as you see on the right over here. What kind of microfacets, the thing we should consider here is what kind of microfacets will reflect light from a particular incoming direction that we care about and a particular outgoing direction that we care about. So for example, if you have a light source over here and you have a camera over here, how much light is actually going to be transferred by this microfacet surface between those two directions? That's exactly the BRDF, of course, right? That's the definition of the BRDF. So the BRDF from incoming direction to outgoing direction is for a microfacet given by this formula. We're not going to get into the details of each of the factors into this formula, but I want to highlight a few of them for you here, okay? And then we'll dig into and focus our attention on the distribution of normals. First, in the numerator, for technical terms, that's a 4 here. There's also an n.I. This is notation for a dot product between n and I and n and O. Those have to do with terms that are related to that follow from Lambertian cosine laws. That's a Fresnel term, which I'll talk about a bit on the following slides. And then this distribution of normals is one that I've already touched on. And then I'll touch on a little bit later when we talk about really advanced material models. This term over here, I'm not going to go into a lot more detail, but I just want to mention it. This is a very technical term and affects the visual appearance of materials in pretty interesting kind of ways. It's a significant term. It's called the self-shadowing, self-masking term. The key idea here is that it considers, okay, for a particular incoming direction and outgoing direction that we care about, and for a particular half angle vector over here, what's the factor of light that's going to be blocked from transfer because of self-shadowing or self-masking? And if you look at this kind of bumpy surface here, you can get a sense for why that might occur. If light comes in at a very grazing angle to the surface, that is a very very close to the plane of the surface itself. If it actually looked like this surface here, well, all these tiny little bumps are going to start looking, like pretty tall, protrusions relative to the traversal of those rays of light at the grazing angle. So increasingly grazing angles, the light that comes in here is going to shadow other parts of the surface. Or in other words, the reflection is not going to be able to go through from one point into the outgoing direction at a grazing angle without being blocked or masked because of these bumps, protruding from the surface. This sort of thing can be worked out theoretically for different kinds of distributions of surfaces, and the masking term can be calculated in order to analytically to provide different kinds of functions for this G to be plugged in. Okay, I want to talk about the Fresnel term. The Fresnel term is really visually significant because it's a strong characteristic of the way of a lot of natural materials reflect light. For example, if you take this scene here, here's some kind of glossy wood table. There's a book. All that's happening here is we're taking photos of it, okay, first from pretty high up. Notice that you don't see the reflection of the wall, the white wall against the dark book very clearly in this, in the wood. And then we take another photo that's a little bit, angled down, and then one that's angled very close to the surface of the table. And notice the dramatic increase in the amount of light reflected off that table, how much brighter the light is on the wood tabletop from the white wall and the dark cover of the book. So reflectance increases with grazing angle for this particular scene. And the general class of materials for which this occurs are called dielectrics, things like plastic materials, glass materials, things like this. This is a dielectric curve for an index of refraction of 1.5. And so some type of glass material. And the horizontal axis is the angle from the surface normal. So 0 degrees means that the reflection direction is sort of like in the original picture, kind of coming down from a pretty high angle, close to the surface normal direction, 0. And as you get to 90 degrees, this means that the surface normal is pointing up, and the angle of incidence is close to 90 degrees, means it's like coming very at a grazing angle on the surface of reflection. These curves just show that the reflectance, the amount of light reflected, goes way up for a dielectric as you approach grazing angles, okay, as you saw in the previous photos. For conducting materials, for example, metals of various kinds, the Fresnel term is very different. Okay, this Fresnel formula is high reflection even for surface angles that are close to the surface normal, and of course high as you get to grazing angles as well. So this gives part of the visual appearance of dielectric materials like plastics and glass, gives them their visual difference from things like metals. Okay, putting all that together, the microfacet BRDF formula that I showed you before, I'm going to show you a few examples, okay? All of the materials in this scene, which is rendered, are modeled with the microfacet BRDF. They have different parameters for the Fresnel term, for the distribution of surface normals, and the self-shadowing term, but they all model with different parameters on that BRDF, that microfacet BRDF. So you can see things like chrome, like glass here, shiny plastics. On this model of this motorcycle, you can see things that look like leather. Some objects over here look more like plastics, so on and so forth. Okay, even the stone in this scene in the background can also be modeled with this kind of microfacet BRDF. It can model things like this wood, which, as you notice, it looks like wood that has like a lacquer layer on top that has been kind of polished with steel wool, so that it's semi-glossy, not very shiny varnish. All of these kind of visual material characteristics can be captured and modeled with this kind of material. Okay, the next thing I want to talk to you about is anisotropy in BRDFs. Up to this point, everything we've looked at actually in terms of materials have been isotropic BRDFs. So to start, let me give you an example of an anisotropic BRDF by looking at metal reflection. Okay, so far, if you have a point light source in any metal that we've looked at in most of our scenes, the highlight, the shiny reflection highlight on it has looked round or elliptical as the shiny spot. But we should know that there's lots of reflection highlights, particularly on metal surfaces, that look very different from that. Here's an example, okay? It's inside this elevator. There are metal walls on the elevator, and there's point light sources right in the overhead of this elevator, very typical elevator setup, lighting setup. And the light sources in the ceiling are not reflecting as like some tiny little perfect mirror reflection of the light source, or even a broad circular reflection. No, they're very different. Can you see this? They're reflected as these broad linear curved bands of light. Okay. This is very, very different than the kinds of reflection on materials like metals that we've seen so far. Here's some other examples. On the left is an isotropic Christmas ornament. It looks like a semi-glossy or even fairly matte diffuse reflection. On the right-hand side is an anisotropic reflection. You've seen these kind of Christmas ornaments yourselves, perhaps, but they're made by taking like strands of threads and tying them at the top and then stretching them around the ball and then putting them in with a needle into the bottom. Okay, many of these strands. And they make these reflections that are very interesting. So the point light source overhead on these Christmas ornaments is doing what? It's creating a highlight that looks like a circle. Can you see that? Two circles in it, as a matter of fact, in this case. And as you rotate this ball around, that circle is always going to start at the top and come down into the ball somewhere and then rotate back up to that circle point at the top. Here's some other examples. Anisotropic BRDFs, brushed metal. You can kind of get a sense, it's really the microstructure of these BRDFs, microstructure of these materials that's creating these different reflection effects. And if I show you this picture actually, and you observe this kind of very characteristic reflection pattern on the bottom of this steel pot versus on the side of this steel pot, notice that the light on this side is being reflected into a vertical line, whereas in the bottom, it's being reflected into like these radial lines that emanate from the center point, right? How are these pans being brushed? I think you can probably guess you've seen these types of materials before, or you can almost perceive it from the reflection. On the bottom, it's as if this metal has been sat on some kind of lathe. It's been spun around, and then it's been ground away with abrasive materials that trace out concentric rings in the bottom, okay, around in a circular pattern as it's been spinning. On the sides, the pot has been spinning and some kind of abrasive material has been put on its side. So it's got grooves that run circularly around the cylinder, okay? Those different patterns, circles, concentric circles in the bottom, or concentric circles around the cylinder on the left-hand side lead to these very different reflection functions. Where it all emerges again, if you look here, this is a picture of the kind of microfacets. This is a depiction of the isotropic BRDF microfacet distribution, a very even distribution pattern that over here, this is the BRDF. We fix the lighting, sort of a light source that comes straight down on the surface, and then consider how much light is scattered in different directions. You can see it's scattered pretty equally in all directions. For this anisotropic material where it's grooves, it's like kind of been scratched in a microscopic kind of a way. If you have light that falls on to this surface, it's going to get scattered preferentially as you can see on the right-hand side here, into a line. Okay, so a point light source comes in and gets scattered into a line, but not vertically. In particular, anisotropic BRDFs have the property that in this BRDF that we know took the incoming direction and the reflected direction and asked how much light was transferred, all four of the dimensions in that matter. That if you consider the incoming direction and outgoing direction in spherical coordinates, so theta I and phi I and theta r and phi r, all four of those matter in terms of how much energy is transferred in this anisotropic BRDF. Whereas for isotropic BRDFs, one of those dimensions, it turns out, doesn't matter. There's symmetry, okay? So in particular, the radial direction about the surface, like it doesn't matter if you take that anisotropic material and you spin it sort of horizontally around, it's going to look and reflect the same amount of light, irregardless of its rotation direction, but not so for an anisotropic material. So in the isotropic material, phi r minus phi I is all that matters, and the BRDF is actually really a three-dimensional function, not a four-dimensional function. Anisotropic BRDFs are very common in the world once you sort of start looking for them. Nylon or most textiles have some kind of microstructure that preferentially scatters light in certain cardinal directions more than others. Some types of materials, like velvet, for example, actually have fibers deliberately that are sewn in a way so that they stick out of the surface. And then the reflection depends on how the surface has been brushed or combed. So for example, you know, you're kind of seeing like microfiber sofas. If you kind of brush them all in the same way, they look a lot neater. If you don't brush them, then they kind of can have sections that sort of reflect light in different sort of random directions based on the orientation of the surface hairs. Okay, so that's sort of some of the nuts and bolts core stuff in material modeling and reflection that I want to cover for you. And then in the time that I have remaining, I wanted to give you a blitz tour of really advanced material modeling topics, okay? And sort of some of the visual richness that we see in graphics that comes from these really advanced topics. So ready for it here? Let's have a look. These are slides that are courtesy of Professor Ling-Chi Yan. He's a professor at UC Santa Barbara. He's formerly a PhD student here at Berkeley and did some phenomenal work in computer graphics on modeling materials, advanced materials in increasingly accurate ways. Let me give you a flavor for how some of this stuff looks. Some work has gone into looking at the details and glints in material. Why? This is the microfacet model that I already told you is very common in graphics, and it is a very flexible, extremely useful material model. But if I show you this rendering of some, surrounding scene in, some kind of natural lighting environment into this teapot, something may not look entirely natural about this. In particular, if I show it to you that looks in a way that looks more like this is what like you can perceive like these fine scratches over the surface. Or this one, which is not really scratches so much, but sort of like fine grooves that have been polished in this teapot in the metal in order to create grooves that are running around the circumference, right? These tiny little details, if you can perceive them, create this glinty effect that is characteristic of most of the real materials that we see in our world. In order to do this, the microfacet BRDF was averaging all of that detail, of those glinty details out. It was taking a statistical norm or a statistical average of that kind of normal distribution function. But if you look at really high resolution normal distribution functions, they're not just like a Gaussian distribution of normals, but they have a lot of microstructure based on exactly the distribution of those microfacets in the material that we care about. If you take care to include all of that, which can be very challenging because you might need very high resolution normal maps, something like 200,000 by 200,000, pixel maps of the surface normal microfacet distributions. That's how you can create these glinty effects, such as you see in this glinty reflection on the snail here, or this version with metallic flakes of colored paint embedded inside or just below the surface of this, this purple reflection here. You can see it in ocean waves, the kind of glints that we're talking about. Here again are the normal distribution function and then a visualization of the reflected light and many, many other examples. So glinty materials are a big topic in the most advanced material modeling and computer graphics these days. The second topic I want to share with you is hair and fur. This actually has a really rich history in computer graphics. It's gone through multiple stages of research development over the decades. First, the thing to note about hair and or fur for that matter is that its reflection off fibers, like really thin fibers and a population of fibers, it also has some very specific visual characteristics. So for example, here, if you look at this person's head, there's some kind of light source off and to the back and left here. And you can see it's creating kind of like the anisotropic materials that I showed you before, almost like the Christmas ornament. It's creating a highlight that is circularly shaped because all the hair is emanating from the colic at the top of the scalp. But if you look closely, you can actually see there's multiple layers of sort of highlight reflection. There's sort of a gold band here, and then there's sort of a wider band, a more, a neutral white colored band over here. So there's a lot of really interesting visual effects that come out in hair appearance. A first attempt, a very important research attempt to model this was the Kajiya-K model. They made some interesting observations that, for example, if you consider the fiber to be a very, very skinny fiber, and you consider light that's coming down that happens to reflect off that fiber, then it will reflect if the material is glossy in a glossy lobe, as you can see depicted here. But if the material is very, very tiny, also this ray of light can strike anywhere around the sort of roundness, the circumference of this cylinder. And if it bounces at different directions, different positions on that circumference, it won't reflect upward here. It can reflect to the side, or this direction here, or actually even downward if it glances off it at a grazing angle. And you can reason for yourself that a single ray of light coming into the cylinder will actually reflect in a cone of exiting rays. Okay, so that was one sort of key insight that they described there in this. And the angle, there's a few other key sort of angles here, but I'm going to leave those because I want to show you some other characteristics. If you render with the Kajiya-K model, you end up with a lot of the highlight structure that I described, and in particular that a cone of reflection gives a lot of the visual characteristics that one actually sees in being able to view light from different directions and not have the highlights change very dramatically. But it turns out that more complicated models, this one's called the Marshner model, capture further facets of the true biology of hair, if you will, and that explain further characteristics of the reflection, the visual reflection, appearance of real hair. The Marshner model uses microscopically this scalloped appearance, as you can see here. It doesn't assume a smooth cylinder, but rather one that's shaped like this. And it theoretically derives that a ray of light that arrives at the surface will then reflect into multiple cylinders, multiple cones of reflected light, as you can see here. One that's labeled R over here, that's the Kaguya K1. A second one that's a cone that's called TT over here. A third one that's called TRT, and even more, but they get darker and darker. The way this emerges is to think of light as a glass-like cylinder, but that as it grows, physically speaking, anatomically speaking, it grows with cuticles. And in terms of the cylinder, anatomically speaking, there's a cortex, that's an inner core that absorbs light, and an outer cuticle, layer of cuticles that reflects light. If you had this sort of a model, then and the cuticles forming this kind of scalloped outside appearance along the length of the cylinder, then you end up with these different labeled reflection directions. R is reflecting directly off the outer surface. There's a change in the angle of it because of that scalloped nature here. There's a TT that transmits into the inner core of the fiber and then transmits by refraction out of the outer core. Some of it will be absorbed by the cortex. And then there's reflections that are TRT that transmit in, reflect off the back surface of the cylinder from the incident direction, reflect back inside, and then refract back out and transmit out into the world again, okay? And that will get double absorption through the cortex. If you incorporate all of those in the Marshner model, then you end up with even more realistic renderings of hair, okay? As you can see here. Maybe I'll have a very short, this has been incorporated, this kind of hair model, it can be incorporated into real-time renderings, such as you see in various games these days. Another one, just to draw this out in rendering a fur, has been drawn into taking more and more and more anatomically accurate versions of this. So from looking in things like FBI reports that study like fur fibers and the kind of inner structure of different types of animals' fur when you dissect them at the microscopic scale, we find that you can't really represent a fur as through the Marshner model. You sort of need a bit more structure. In particular, the reason is that fur fibers, it turns out, for things like cougar or most animal fur, have an inner structure that's a bit more complicated than for human. There's a cortex, which is true in human fiber, but in the human fiber, there's an inner structure, the very center, called a medulla, that's very small and sort of not well developed. But the medulla is pretty large and well structured in fur. So for example, in a cougar, you can see the inner medulla here has lots of tiny little air pockets in it. It really absorbs and scatters a lot of light. So the inner medulla is large in fur. If you take this into account, then you can render objects that look a lot more like fur as opposed to hair. So here's a hamster with 600,000 fur fibers. A lot of samples are required to resolve this. The punchline here is that, to do rendering for fur for a lot of the kind of special effects that I see in the movies these days, maybe the poster child being the Planet of the Apes, which, by the way, won an Oscar nomination for Best Visual Effects based on this rendering of fur. You need to have this kind of a advanced fur model that has a twin core, a cortex, and an inner medulla in order to capture those reflections of light in the fiber correctly. All right, and then we're almost at time. I was going to show a couple of pictures. The last thing is participating media. This is a volumetric effect. It's things like fog, things like clouds. To do it is kind of like the ray tracing, recursive ray tracing off surfaces that we've talked about, except that you have to recognize that you can't just trace a ray freely through air until it hits another surface, but rather with every tiny step that the ray is taking through, like a cloud or through fog or through steam or smoke, it's going to interact with that material it's going to be partially absorbed by that material. It's going to be partially scattered or reflected into different directions by that material. So you have to have volumetric reflection functions. And when you do ray tracing in a path tracing sense, you can't just trace paths from surfaces to surfaces, but rather you have to trace paths from volume position to volume position, and it gets very computationally intensive very quickly. Okay, so it's kind of like this: paths through clouds, not just over from surface to surface position. If you do this, though, you can render really compelling pictures of scenes, and things like clouds, little bits of atmospheric steam that are in different scenes, and they can add a lot of visual realism to the kinds of worlds that we know about. Okay, I have one more thing I was hoping to show you, which is translucent materials or subsurface scattering, as it's called. Things like jade, jellyfish. I was going to tell you a bit about what's the difference between milk that has subsurface scattering and translucency as opposed to paint, okay, titanium paint, which does not have subsurface scattering. And you can see visually what it is, what it looks like here, very clear to us, right? Skim milk versus titanium paint. In order to simulate that, people have worked out a lot of these kinds of things that allows you to render things instead of with BRDFs that look like painted on, a white painted marble statue. If you want it to look like marble, the bleeding of light into the marble a little bit before it then scatters back out and exits the surface, you need to be able to simulate that properly in order to make it look like marble correctly. Or if you want skin to look a little bit softer, the way that it does visually to us in the real world, you have to take that into account as well. All right. Just sort of got to the end. All right. Sorry to keep you 1 minute extra. Great to see you all, and see you again soon.
Ren, there was a question